In the first lecture on support vector machines, we saw how to solve that problem of maximizing the margins and the resulting complications from having discontinuous derivatives. So this led us to a formulation of the problem, the support vector machine, which now we're going to see has some interesting properties that we can use to go beyond a simple linear classifier. So now we're going to look at soft margins, which is allowing some points to violate the margin constraint, and then the kernel trick that allows us to implicitly expand the data into higher dimensions and do the same thing that we did with logistic regression explicitly, but now in a much more efficient way without having to actually do the transformations on the data. And then we'll see some issues about regularization in support vector machine to try to optimize the performance. So let's first consider the formulation that we saw previously. So we converted that problem of trying to maximize the margin into this optimization, where we're going to find the values for the alphas. Remember, the alphas are the Lagrangian multipliers that come from imposing a constraint that each of our points in our training set must be at least one away from the discriminant. So the optimization problem is to maximize this expression on all of these alphas. And this has two terms, the sum of the alphas, and then this penalty depending on the product of, for each pair of examples, the product of the alphas, the class labels for that pair, which we consider to be plus or minus 1, and the inner product of the vectors for those two examples. And this is subject to a constraint that the sum of the product of the alphas and the corresponding classes must be 0. So since these classes are minus 1 and plus 1, this means that the total alpha for the positive class must be the same as the total alpha for the negative class, the total sum of the alphas. And since they are Lagrangian multipliers, they must be all at least 0 or positive. So we saw how we could solve this, and this would give us a result, for example, like this with this data set, where these 3 points, which are the support vectors, have an alpha greater than 0. All the others have alphas of 0 because they are irrelevant for determining the position of the discriminant. So this is how a support vector machine works, by solving this expression here, finding the maximum for this expression. We identify the support vectors and we obtain the alphas for these vectors, which in turn allows us to specify the position of the discriminant. Now, this works if the classes are linearly separable. If the classes are not linearly separable, then the constraint that we required, that the closest points must be at least some distance away from the margin. Note that this distance is measured in terms of the vector that we have for determining the position of the discriminant. So no matter how close they are, we can still increase the size of the vector and solve the problem. But if the classes are not linearly separable, then this will not have a solution. Or we can see here intuitively, if we have points of different classes that are close together, so their dot product is high, their classes are different, so this is negative. So the contribution here, when we take into account this signal, this minus sign here, will be overall positive. Then if there are many such cases where we have points from different classes in the neighborhood, then it may start to compensate to increase the alpha to infinity. And this will no longer have a defined value for the alphas for maximizing this function, because now it can grow all the way to infinity. So this would be the case here, where we have these points that make these two classes no longer linearly separable, and so there is no solution for this formulation of the problem when we have classes like this. So this can be solved by using soft margins. So instead of having a hard constraint like this, where we require the product of this example multiplied by the vector that determines the discriminant, this expression here, and then multiplied by the class to be at least 1. This means that some examples that belong to the positive class must have a positive sign here, and examples that belong to the class -1 must have a negative sign on this expression, so that this is always positive. And by adjusting the size of this vector, we can then ensure that this is always at least 1. But if this is not possible, what we can do is to soften this constraint. Instead of having a hard constraint that this must be at least 1, we say that this must be at least 1 minus some xi value here that we consider to be positive, and this would be or positive or 0, and this would be a slack variable that allows us to violate the constraint by increasing the size of this variable. So if this point is between 0 and 1, if this xi value is between 0 and 1, this means that the point is approaching the discriminant but did not pass to the other side. But if the xi value is greater than 1, then we can actually allow this point x to be misclassified. So we are saying that the product of the class multiplied by this expression here can actually be some negative value if the corresponding xi value is larger than 1. So this is how we can soften the constraint. And now we want to do the same thing again. We want to minimize the size of this vector, but we add this a function of these slack variables as a regularization term. So we would like these to be as small as possible, but they may be have to be large if the points cannot be all properly classified. So this is our regularization term that we're going to multiply by some c value here, and then we are going to minimize this, the size of the vector as we did before. So what this ends up as equivalent to is that now we have these new variables here, these xi variables. We can still write the Lagrangian all the same, and this would be the expression for the Lagrangian, and the result is that when we convert into the dual problem where we have to solve as a function of the alphas, we have exactly the same optimization problem. So including these slack variables to soften the margins does not change what we need to optimize to compute the alphas. But what results is that because we need also to compute the critical points of the Lagrangian when the derivative with respect to all the xi values is 0, this ends up giving us this expression as a function of the alphas and the Lagrangian multipliers for the xi values, which ends up being equivalent to placing an upper bound on the possible values of the alphas. So with this formulation of the problem, mathematically, adding these slack variables and adding this regularization term to our optimization ends up being exactly the same optimization problem for finding the alphas, with the only addition that now the upper boundary for each alpha is equal to c. So this same c that we are using here. What we have here intuitively is basically that we are placing an upper limit on how much we can penalize points that are violating the margin, because the Lagrangian multiplier is the multiplier that will increase as we violate the constraint. So this would prevent us from violating the constraint by shooting up to infinity. But if we place a limit on that, then we no longer have that problem of having alphas growing to infinity, and we can always find a solution. So if we look at our simple implementation of a linear support vector machine previously, the only difference is now this. While previously we had a none here because there was no upper boundary for the alphas, we now have this constant c, which is this regularization constant, that if it's higher, then it means we have less regularization. If it's lower, then we are regularizing more because we are imposing a stricter limit on the upper bound of the alphas. So let's see the result in this case. Even if the classes are not linearly separable, if we limit all the alphas to a value of 10, a maximum value of 10, we can find a solution. This is the discriminant. This will be the margins. And now we have some points here that are support vectors that still meet the margin constraint. So these three with black circles around them. And then we have other support vectors here in red that are violating the margin constraint. And if we look at the values of the alphas, what is happening here is we have some, the alpha is varying only between 0 and the maximum of C. So all of these are support vectors. They have alphas larger than 0. So we can use them all to compute the vector that is perpendicular to the discriminant here. To compute the W0, that additional constant that determines how high or low this discriminant is, we should only use the vectors for which the alpha is lower than C. This is because this expression here, which we are going to use to get W0, is only valid for these support vectors that are on the margin. And these support vectors that are on the margin have an alpha value that is greater than 0, but was not raised up to the limit of C that we imposed. All of these that are violating the margin have a maximum penalty of C in their alphas. So this way we can compute the W0 using only those support vectors for which alpha is below C, and discarding those for which alpha reached up to the value of C. But this, in practice, actually explicitly computing the discriminant is not something that we will generally use in support vector machines, because this can only be used with a linear support vector machine like this. And usually support vector machines are applied to problems where we don't do linear classification, as we're going to see a bit further on. So in this particular case, we can see the actual results of the alphas we got in the optimization here. We can see that most of them are close to 0. Here, 10 raised to minus 15, minus 12, minus 14. So these are 0 in practice. It's just a matter of small rounding errors. Then we have this is 6.6, 5.8, and there should be another one here, 2.5. So these are the three support vectors that lie exactly on the margins, the ones that are marked here in black circles. So these are support vectors that are not violating the margin constraints. And then we have these other support vectors here, 10, here again 10. So these are 10, which is the maximum we allowed for alpha. We use the C value of 10, and this would be the upper limit on the values of alpha. So these have reached the upper limit because they are violating the margin constraint. So if we did not have regularization with that C value, in this case the alphas would shoot to infinity, but because we set this hard limit on the values of alpha, these ones all reached that top. So these are support vectors that violate the margin constraint. These others are support vectors that lie on the margin. So you can see this a bit better here. I marked with black circles those that lie on the margin. So these have a value of alpha that is greater than 0 but lower than C. And then these red here are support vectors that have violated the margin constraint. The ones with the red full circles that belong to the red class because they are higher than they should be, and the ones in blue because they are below this margin here. So in one case, this one is actually misclassified because it's below the discriminant also. Now, how can we extend support vector machines to do a proper separation of non-linearly separable classes? If we have something that is like this is almost linearly separable, but there is only a slight problem there, then maybe we can do this with a linear classifier. We will have one error there, but that's not a big deal. So soft margins can be okay if we have a slight overlap of the classes here around the linear discriminant. But if we have something that is the frontier is very far from linear in the original space where we have our data, then soft margins will not be appropriate. So we could obtain a linear discriminant here with the support vector machine. By using soft margins, we will have a large number of support vectors that are violating the margin constraint, but the classification here would be very poor because the frontier between these two classes is very far from linear. So we need something to solve this, and we already saw how we can solve this problem. We can expand the features. For example, as we did with logistic regression, we used some polynomial expansion. We just multiplied the features, but any nonlinear expansion would do the trick. And we could expand the features nonlinearly to a higher dimensional space and then do a linear classification in that higher dimensional space. And this is where support vector machines really give us a big advantage, because they make it very easy to do this at a low computational cost and implicitly using this kernel trick. Now, unfortunately, the name kernel is used in different contexts to mean different things. So it can be the part of a matrix we use for some multiplication. It can be, as we saw previously, a symmetrical function with an integral of 1 when we saw kernel density estimation. And here it means something differently. So it's the same name, unfortunately, but has a different meaning. A kernel function in this context is a function of the two vectors, the inner product of two vectors after some transformation. So we take the vector u, transform it with this function here, and do the inner product of the transformation of v also. So this could be a transformation like a polynomial expansion, for example. Suppose that this phi function was this one here, where we take the vector x, which has two coordinates, x1 and x2, and we create a vector like this with 1, square root of x1, square root of x2, this square root of 2 times the product, square root of 2 times x1, x2, then the product of both of them, the square of x1, the square of x2. So this would be an example of a polynomial expansion where we are creating here polynomial terms. We have these nonlinear parts here, so we are twisting the expansion in this new higher dimensional space. But we can easily compute the result of the inner product of these two transformed vectors by using this kernel function here. So this would be just using the inner product of the original vectors and then adding 1 and squaring the result. If we did this, we get the same thing as applying this transformation to each of the vectors and then computing the inner product. And as you can see, this is much simpler to compute. So if we have a function like this, a kernel function, that gives us, as a function of the original vectors, the same thing as the inner product of their transformations, then we can simplify these inner products. And since the expression we want for solving the support vector machine, for computing the alpha values, only has the inner product of the examples, it doesn't have the examples isolated, but also always the inner product of pairs of points, then we can use the kernel function to compute this inner product as if we had applied some complex transformation to each of the vectors. However, since we have this kernel function, we don't need to apply the complex transformation. We can just use the kernel function. So in this case, for a polynomial expansion to degree n, we just need to compute the inner product of the vectors, add some constant, and raise to the power of n. And this is much simpler to do than to do explicitly all of these transformations, which would lead us to very large dimension vectors if we have a large n here. So this is the kernel trick for support vector machine. It takes into it makes use of this property of what we're trying to maximize, which is all the examples appear only as inner products of pairs of examples. And by using the appropriate kernel functions, we can do these expansions implicitly without having to compute them, just by using the kernel function on the original vectors. So basically, if we have a kernel function that simplifies the computation of the inner product after the transformation, we can take advantage of that to use that transformation without more demanding computations, without more inefficiencies like that. Okay, so we can now solve the same expression, only instead of using the inner product of the original vectors, we use the result of the kernel function, which gives us the same thing as expanding our data using those transformations and then computing the inner product after this transformation in this space of whatever function we use to transform them. So when we do this, we now have a linear classification in this higher dimension after these transformations, but we do not have these transformations computed explicitly. This is the advantage of support vector machines, which is not requiring us to compute these transformations explicitly. So we are unable to compute the vector for our discriminant or that constant there, because the linear discriminant only exists in this higher space after the transformation, which we will never look into explicitly because it can be of very high dimension, in theory even of infinite dimension. So instead, we can just classify each new example. So if we have a new example x, we can use the support vectors to classify this new example by computing the kernel function for each support vector with our example that we want to classify, multiplying by the corresponding alpha and the class label, and then summing everything. So since this is the same as the value we would obtain in this higher dimension when looking at the expression for the discriminant, this also tells us if we are in the positive class or in the negative class. So we can use this for classification without having to compute explicitly these parameters of the discriminant. We only need the alpha values for the support vectors. Because the others will be zero, we can even discard them. So basically the idea is that when we use a support vector machine with the kernel trick, we compute all the alphas as usual, and we store the support vectors and their corresponding alphas. So for those alphas that are greater than 0, we keep those examples and the alphas. And when we need to classify a new example, since we don't want to compute explicitly the discriminant or to explicitly do these transformations, we can just use the support vectors and check the sign of this expression here. If it's positive, then our example is classified in class 1. If it's negative, then it's classified in class -1. So let's see how we could change our implementation and adapt it to using a kernel function. So let's say that we are using a polynomial expansion. So we use this polynomial kernel function that allows us to expand implicitly to a polynomial expansion of degree d just by computing the inner product of the examples vectors, adding, for example, 1 and then computing this raised to the power of d. So we could, when we are computing the age matrix, the one where we would put all the inner products multiplied by the class labels, we can just, instead of the inner products, use the kernel function here and then multiply by the class labels, and we return the new value age. So now we could just solve the same expression for the support vector machine. So this maximization here in order to obtain the alphas. And then we would store the support vectors. And when we need to compute, to evaluate a new point, so classify a new point X, we would loop through all the support vectors, add this product here, the alpha, the class label, and the kernel function between this particular example on our training set and the one we are trying to classify, and then check the result. So if this is positive, it will be class 1. If this is negative, it will be class -1. So we will not do this ourselves. It's always best to use the scikit-learn implementation. So you can import this module, SVM. You have this support vector classifier, SVC class here, where you can specify what kind of kernel you want to use, the parameters for the kernel, and the regularization term here, that C value for the soft margins. So if you use a very high C, this is a very low regularization because you allow the alphas to grow to very large values. If you use a lower value of C, this is a stronger regularization. And this is why then in other classifiers, you will also have this convention of using a large C for smaller regularization and a lower C for stronger regularization. And now this object works just like the other classifiers. You have a fit where you present the examples as a matrix, where each example is a row and each feature is a column, and then the class labels, which can be a vector here. So the reason for showing you the implementation details is only for to help understand the algorithms. In practice, we will not implement these by hand. We will use the optimized version in scikit-learn. So this is an example of classifying this data set with strong regularization. So we have very soft margins here, and we use a polynomial expansion of degree 2. This would be if we increase the polynomial expansion. So you see we are increasing the dimensionality of the space to which we are implicitly projecting our data, and so the curvature here can increase. And if we increase the C value, we are imposing increasingly tighter margins because we increase the maximum value for the alphas, for the penalization. And so if we have a very high C, we force the margins to be very small, but we prevent points for violating the margin constraint. So in this case, we have less regularization, the curvature is much tighter, the margins are much smaller, but we still can classify properly these points because we are using this kernel expansion to implicitly do a linear classification in a much higher dimensional space after this nonlinear expansion. There are other kernels, for example, in the radial Gaussian radial basis kernel uses a kernel function that is a function of the distance between the examples with something that approximates a radial Gaussian distribution. In scikit-learn, the expression is slightly different. So here, if you were to use the original expression for the Gaussian radial basis function, you would have a sigma value, which is the variance or the standard deviation here. So sigma squared is the variance, and you would divide by that value before raising e to that number. With in scikit-learn, this is replaced by this gamma parameter. So gamma is 1 over twice the variance of the Gaussian curve that we are considering here. And this, in fact, is the equivalent of expanding our data into infinite dimensions using this type of radial basis functions. But since the kernel function is very simple, we can use this and we can adapt our data as much as we like, because since we are looking at distances between vectors, we can adjust the discriminant to take into account different neighborhoods of where our data is placed. So this would be an example with a very small gamma. Remember that gamma is inversely proportional to the variance of the Gaussian curve. So this would be like we were using very large Gaussian curves on top of each point. And so we smooth everything a lot. And if we use a low value of C, we have very strong regularization here. So this would not be a very good option, probably, but you can see the effects of using a very low gamma and a low C. We have very large margins, and this is almost a straight classifier in this dimension. If we increase the size of gamma, we are decreasing the variance of the Gaussian curves, and so this is a bit like decreasing the neighborhood in k-nearest neighbors, or decreasing the bandwidth of the kernel we use in kernel regression. It has a similar effect, and as we increase gamma, we are taking into account closer and closer neighborhoods when deciding the classification. So, for example, here with gamma equals 2, we have a margin here, and we start having margins here. So we are already considering that these parts are close to the discriminant and are beyond the margin. So you see, you can have a very powerful transformation of the data with this kind of kernels. If we increase the value of C, then in addition, we also are decreasing here the size of the margin. So if we have a C of 1 here, we can have a fairly large margin. If we have a C of 1000 and a low gamma, we have a smooth discriminant here that is not very curvy, but the margins now are growing shorter. If we increase the size of C and also increase the size of gamma, not only do we allow for tighter curves, but we also force the margin to be smaller. So this way you can control how the margins behave and how the expansion is done implicitly by the support vector machine. And so by adjusting these parameters, you can adjust your classifier easily to any data set that you want. Of course, remember that there's always the problem of overfitting. So if you adjust too much to the training data, then you may lose the ability to generalize for other data, but that is a generic problem. The big advantage of support vector machines is that they allow us to do this kernel trick, where we can implicitly and with no or nearly no computation costs expand our data into a very large number of dimensions and solve difficult problems for other classifiers. So just before I summarize this lecture, I just want to talk briefly about this first assignment. You're going to use a data set that has 4 features, so it's a 4-dimensional data set. That means you will not be able to do this sort of plots. These plots are good to illustrate the concepts in the lectures, but in reality, they can only be used if you have 2-dimensional data, and that's generally not the case in practice. So in this case, you're going to use 4-dimensional data. You have features extracted from scans of banknotes, and the idea is that some banknotes are fake, some are real banknotes, and you need to train the classifier to be able to distinguish them from these features obtained from the scans. You're not going to do manual expansion. Remember that those things that we saw for logistic regression was mostly for illustrating the concept. There will be a few cases where you actually need to do manual expansion of the data, because if you want to do nonlinear classification, then it's best to use something like a support vector machine, where this expansion is done implicitly and automatically in the classifier. So here you're going to compare 3 classifiers. A naive-based classifier using kernel density estimation for estimating the probability distributions of the features given each class, and this will be implemented by you. You will also compare this with the Gaussian naive-based classifier that uses this parametric distribution and is implemented in scikit-learn, and with support vector machines that you're going to use also from scikit-learn. So the only classifier you're going to implement will be this version of the naive-based classifier with kernel density estimation, and even the kernel density estimation you can use the one from scikit-learn. So you just implement the part that is respective to the naive-based classifier. You're going to optimize parameters, the bandwidth for the kernel density estimation in your naive-based classifier, and the C value for regularization in support vector machine. So you're going to use always the same kernel and just adjust the C and compare these three classifiers that you obtain using the approximate normal and the McNemar's test, the two tests that we saw, and then discuss your results if one is better than the other and so on. So for the discussion, you have this question form that you can download either in English or Portuguese, as you prefer, and you need to fill that questionnaire. You also need to send in the plots, they are in the instructions, and to submit your code. So everything is in the instruction page. Check it for the details and eventually for updates if I need to clarify something that was still not clear in the instructions. But this will be your first assignment. Check the page for the dates and for all of these details. Okay, so to sum up this part, what we saw here is that starting from that formulation of the support vector machine and how we can solve the maximum margin problem by computing the Lagrange multipliers, the alphas that maximize that expression. We then reach the conclusion that we can soften the margins by using these slack variables by allowing some violation of the constraint with some regularization. We don't allow for arbitrary violation of the constraints, but the end result is the same. It's just that we impose an upper limit on the values of the alphas. And also, since we are only using inner products between pairs of examples, we can use the kernel trick, using kernel functions, to implicitly expand our data into higher dimensions without having to actually compute all the expansions of our data. Because since we only need the inner products in those higher dimensions, if we have a kernel function, we can do that computation very simply. So we saw this using soft margins for regularization and the kernel trick for extending support vector machine to a nonlinear classifier. There are some sections here in these books that you can read for more details on support vector machines.